All right, in this video, we're going to start talking about what series are. We're going to look at some of their properties and some summation formulas. A series is basically a sum of a particular number of terms in a sequence where I'm given using sigma notation, and we are looking in the function that you have inside a sigma is going to be the explicit form of some kind of sequence, where we are looking at, you start with the number that's on the bottom, and that's going to be the number that you put in first, and it's going to give you your first number, and you're going to work your way up, increasing this number by 1 each time until you get to n, because a series is a sum of a number of terms. Now, the way that you would read this is that the sum from I is equal to 1 to n of whatever this expression is equal to, and then whatever our sum is. The variable I, in this case, it could be any variable, is called the index of summation. And we're going to start working our way trying to find sums, and then we're going to progress forward into some more complex ideas going forward, where we would look at some convergence or divergence of some series like we did for sequences in some later videos. So let's look here at this first example on the left-hand side, and I'm given the summation from n is equal to 1 to 4 of n times n minus 1, and I want to rewrite as a sum, and then I want to evaluate. So we want to expand this series. You start by putting this first number in for n and writing down what you get. So we get 1 times 0, and so our first number is 0. And then plus, then we increase the size of n. So that was when we put in 1. Now we're going to put in 2, and we're going to put back in, we're going to reevaluate. So it'd be 2 times 1, we get 2, and then plus, now we're going to put in 3 to see what we get for the n. So we'd have 3 times 3 minus 1, 3 times 2 is 6. And then plus, we keep going until we put in 4, which is the top number of this series, and we put in 4. 4 times 3 gives me 12. So I expanded the series. Now we add up all those numbers, and so the sum of that series is going to equal 20. Now let's do this again for the series over here on the right-hand side. So I want to find the sum of the series from n is equal to 1 to 5 of 4n squared minus 3. We'll start by expanding the series. And so I'm going to start, I put in 1 for the n's, and I see what I get. When I put in 1 for the n's, I get 1. And then plus, I put in 2 for all the n's. So 4 times 2 squared minus 3 gives me 13. And then plus, I keep going. Now I put in 3 for the n. So 4 times 3 squared minus 3 gives me 33. Plus, now I put in 4 for the n's. So 4 times 4 squared minus 3 gives me 61. And then we have to keep going until we get to that top number of 5. Put 5 in. 4 times 5 squared minus 3 is 97. So we expanded it. Now we add all of our numbers together, and we get 205. All right, now we're given a series that's expanded. We want to write this series using sigma notation. So basically what you have to do is you have to write an explicit form for the series that you're given. So I look at it in terms of a sequence of terms. So let's try to find a pattern that exists within the numbers that we were given. And so if I'm looking to go from 3 to -6, -6 to -15, I'm basically subtracting 9 every single time. And so I could write an explicit equation for this and say an, this is an arithmetic sequence, which would be a1 plus d times n minus 1. And so our first term is 3, our common difference is 9, so 3 minus 9 times n minus 1. And you don't really have to simplify that, because we're just trying to write a summation. So I'd write this as the summation from n is equal to 1, and we'll worry about the top number just a minute, of our explicit formula, 3 minus 9 times n minus 1. Now the number on top is, well, how many terms did I have? 1, 2, 3, 4, 5, 6. So my top number here is 6. There's our sigma notation. Now let's look here at this next one. So I'm given the expanded series where I go 3 minus 6 plus 12 minus 24. Treat them like a sequence of numbers and find the pattern that exists. So to go from 3 to -6, -6 to +12, +12 to -24, we are multiplying by -2 every time. Well, that is a geometric sequence, if I look at it in terms of pattern of terms, which would be a1 times r to the n minus 1 power, which I could write a1 is the first number, 3, r is negative 2, raised to the n minus 1 power. So our summation here, we'd have the summation of a certain number of terms, starting with the first one, of this explicit formula, 3 times negative 2 to the n minus 1 power. And I got to figure out my top number. Well, how many terms did I have? 1, 2, 3, 4 terms involved. So the top number here would be 4 in our sigma form for the summation. Now let's look at this next one. So I have a half minus a third, plus a third minus a fourth, plus a fourth minus a fifth. So I'm going to treat these like individual terms here. So I want to come up, why did I pick that? Because summation is adding, so I see what I'm adding here. And so my first term is going to be that first set of parentheses. My second term here would be the second set, and my third term would be the third set of parentheses. And if I'm looking in terms of, all right, well, how would I write this? Well, I have 1/2 minus a third, and then a third minus a fourth, and a fourth minus a fifth. Well, what if instead of looking at this in terms of n is equal to 1, 2, and 3, all right, I have them grouped in terms of what they are, but I need to make two fractions. So I have 1 over something minus 1 over something else. Well, if I started with 2 for this first set, I could say it's 1 over n minus, and then 3 is n plus 1. And then my second set, if n was 3, it would be 1 over 3 minus 1 over n plus 1, which make 1 over 4. And this third set would be if n was equal to 4, because I'd have 1 over n, so 1 over 4, minus 1 over n plus 1, make 1 over 5. So here is our explicit formula. Now, we made it much easier to write, but we didn't start at 1 in this case. We started at 2. And so I needed to come up with my top number, and so I'd count starting with 2. So 2, 3, 4, so my top number here is 4. There is a writing the series using sigma, and you don't have to start at 2 or at a certain number always. I don't always have to start at 1 or 0. I can pick whatever's easiest for us in terms of writing our summation formulas. Now let's look at one more. So I'm having the expanded series, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. I want to write an explicit equation. Well, they're all fractions except for this first number. Well, I'm going to make that 1 over 1 and look at what's changing. Well, the only thing that's changing in this case is the denominator each time. And so I could write this, the explicit form would be 1 over n, where I start with the first value of n being 1, and I keep going until the last number I use for n to be 5, and there's our summation. Now we're going to work our way to some summation formulas and properties. Now we've seen when we were finding some sums that yes, we can always find the summation by plugging in for n, but if the top number was very, very large compared to the bottom number, a big difference, I'd have to plug in a lot of numbers to get my summation. And so there are some formulas we can use to kind of get these sums a little bit quicker. However, they are algebra intensive. And so in this chart, I summarize some of the properties of sigma and some summation formulas that we're going to use in doing the next couple of problems. And so let's say I wanted to evaluate this first series by using summation properties and some formulas. Now, all of these are coming from, these properties are coming out of this table here in the summation formula, so I'm going to refer into. So first property we have of summation. Now I'm going to temporarily just let the top number be n. And when I'm doing this is I can break up a summation into the sum of individual parts. Now I cannot break up addition, or excuse me, I cannot break up multiplication, but I can break up adding and subtracting. I'm going to break this up as a summation from 1 to n of 1 plus the summation from I is equal to 1 to n of just I plus the summation from I is equal to 1 to n of I squared. I'm going to replace all of these with their summation formulas. Well, the first summation formula we have is if we're finding the sum of a constant from I is equal to 1 to n, its sum is going to be equal to that constant times n. Now, all of these summation formulas are based on this bottom number being a 1, our index number at the bottom, plus the summation of just I. So according to our chart, the summation of just I is going to be n times n plus 1 over 2. So I have plus n times n plus 1 over 2. And then plus, if I'm adding the summation of squares, I squared, that summation formula is here. And so I'm going to put that in, and I'm going to keep it with terms of all of the n. So we have plus n times n plus 1 times 2n plus 1 over 6. Now we know that n is equal to 8, and so we'll make all of the n's equal to 8. So I have 1 times 8 plus 8 times 8 plus 1 over 2 plus 8 times 8 plus 1 times 2 times 8 plus 1 over 6. And then we evaluate that to get our sum, and we would get a sum of 248. Now let's look at a much harder one. So I want to find the sum of the 20 terms going from I is equal to 1 to 20 of this polynomial expression. And so here, if we were doing this by hand, we would definitely want to use some summation formula so we wouldn't have to plug in 20 times and add all the 20 numbers together. So I'm going to use properties of sigma to break this apart. And so I'm going to let n represent 20 when I'm doing this. So I'm going to go from I is equal to 1 to n of the summation of 3 minus, now we also have properties of sigma where I can pull coefficients out from inside. So I'm going to write this as 4 times the summation of I is equal to 1 to n of just I, and then minus 2 times the summation. I can pull constants out. That's what I'm doing, and multiplying it to their summations. And I'll pull the 3 out here for the last part. I is equal to 1 to n of I cubed. Now I'm going to go in, I'm going to use my summation formulas, starting here at the far left. So to go from 1 to n of the constant 3, that would be equal to whatever 3 times n is. And then I would have minus 4 times, and then the summation of just I from I is equal to 1 to n. We've used that one already, and that is n times n plus 1 over 2. And then minus 2 times, well, I squared summation from I is equal to 1 to n was n times n plus 1 over 2n plus, or times 2n plus 1 over 6. And then the sum of cubes. Well, we haven't used the sum of cubes one yet. According to the table, to find the sum of cubes from I is equal to 1 to n would be n times n plus 1 over 2 quantity squared. And so we'd have 3 times n plus 1 over 2 quantity squared. Now, for us, n was equal to 20. And so we would substitute 20n for all of those n's there. And after substituting 20 for all of those n's, we would evaluate, and we get a pretty large sum here of 125,780. Now the last part here for some properties of summation. Now notice how all of our summation formulas focused on when the index number we started with was 1. Now what if we needed to start with a different number? Let's say they gave us a number that was not 1 and we needed to adjust our explicit formula so that way we started at 1. And what we're going to do is we're going to have a process here. So we want to rewrite the following series so that way we have an index number of 0. Now the process itself is not that complicated, but it's kind of hard to generalize the process itself in terms of a bunch of general terms. So we're going to look here at this first one on the left. I want to rewrite the summation from n is equal to 1 to 6 of 3 times 2 to the n minus 1 power, and I want to write it where I start with n equaling 0. Now what I would do is I need to think of this and say, all right, they have to be equivalent forms. So if n is equal to 0, n is equal to 1 means that I would need to take my current n and I would need to add 1 to it. And so what we're going to do is we would take our equation here, so 3 times 2 to the n minus 1 power. And where n is, I'm going to put n plus 1 in this place. So I have n plus 1 minus 1. So I replace this n with n plus 1, which is what 0 is technically representing. And so by doing that, I also need to figure out and adjust my top number. Well, if I went from 1 to 0 here, that means I need to go from 6 to 5 on top, so I need to take 1 away. And so our expression here for our index shift to go from 0 to 5 of 3 times 2 to the n power. All right, now let's look at this one here. Now, we would have an issue if we were actually trying to find the sum here, because I would be trying to find the sum of a certain number of terms where I start with something that is undefined, because I would have 2 divided by 0. And so we have an issue here, but we're not actually finding the sum, as we're just trying to practice the process of rewriting with an index shift. So I want to go from n is equal to 3 to writing an equivalent form here where n would start with 0. And so I kind of work my way, and I think for a second and go, all right, well, wait a minute. I could adjust my top number. I went from 3 to 0, which means I need to go, I'd be 3 units shorter of 12. So 12 minus 3 would make the top number 9. And I want to come up with a way to rewrite our equation. Well, I'm just going to adjust the variable n. So I have 2 over 3 minus, and now I have to do some adjustments. Well, let's think about what we have. So to go from 0 to 3, we would need to add 3 to 0 to make it become that 3 that we have on the right-hand side, which means that inside of our equation that we originally had of just n, inside of here we would need to have n plus 3. And then we would simplify. So after our index shift, to go from n is equal to 0 to 9, our equation would just be 2 divided by n. And we would attempt to find the sum, but we would have that same issue where we'd be starting with an undefined value. So, but that's in a nutshell of how you would do an index shift.